Hello, AP Physics 2 students. So we are moving into our next topic, which is thermodynamics. But before we can study thermodynamics, we need to talk a little bit about gases. Now remember, gases are a fluid. So all the rules that we have about fluids apply to gases. But gases have some special properties, and we need to know these things before we can really understand thermodynamics. So let's get started. Just as a reminder, these are the chapters in our textbook that cover thermodynamics and gases. So first things first, you remember in class we did a couple of these labs. There's three major labs. One of them is that we took a gas and we compressed it to a smaller volume and then measured the new volume and the new pressure. And from that lab, we discovered that pressure and volume were inversely related. We also did this for different amounts of gas, and we found that the greater the number of moles that were in the gas, the bigger amount of atoms that we had, we would get a bigger PV value. So PV is proportional to N, the number of moles, or PV of the gas, the pressure and volume of the gas, is directly related to the N, the number of molecules in the gas. All right, the second lab we did is that we took a flask, we stoppered it, and we put a pressure gauge and a temperature gauge in it. And then we heated it up and cooled it off and measured pressure versus temperature. And in that lab, we discovered that pressure and temperature were directly related. So as the temperature goes up, the pressure goes up. Now, a lab that we didn't actually have time for in class, but that we could do, was to measure the relationship between temperature and volume. An easy way to do this would be to get a balloon, measure its circumference so you can approximate it as a sphere, and then you can calculate its volume for like room temperature. You could heat it up in an oven and see that it expands, and then you can cool it off in a freezer or refrigerator and measure its new circumference and work backwards to find its new volume. If you do this lab, you'll find out that volume and temperature are directly related as well. Okay, these are common labs that are asked for on the AP exam. This is one of the lab learning objectives. So don't be surprised if they ask you to design a lab to find the relationship between, say, pressure and temperature or something like that. Remember, on the test, if they ask you to do that, even if you already know what the relationship is, you still have to, you can't just tell them that, well, this is the relationship. That's not what they're asking. They're asking you to design a lab to show this relationship. Okay, so you'll have to design the lab even if you know what the answer is already. Now, if we put these three labs together, what do we find out? We find out that pressure and volume together multiplied are proportional to the number of moles times the temperature, or the amount of gas times the temperature. But N and T, moles times Kelvin, that's not the same unit as pressure times volume, Pascal times meters cubed. So we need a constant in here, and the constant that we have is called the ideal gas constant, which is 8.314 joules per mole Kelvin. And so we get this equation right here, PV equals nRT, where N is the number of moles. Now, there's another way to write this. We didn't really use this one in class very often, but it is that PV equals N, the number of molecules in the gas, times KB, which is Boltzmann's constant, times temperature. It's just a different way of accounting for how much gas you have, and so the constant is slightly different. So if you use N, the number of molecules, then we use KB as our constant, and here's the number for Boltzmann's constant. Now, both of these constants are on the equation sheet, so you don't need to memorize them. Okay, so the ideal gas law, PV equals nRT, or PV equals NKBT. Okay, first thing about units. For pressure, the units are pascals, and atmospheric pressure equals, okay, I didn't write it down, so you can look this up on the equation sheet. The atmospheric pressure turns out to be about, on average, across the whole planet, 101,325 pascals. On the equation sheet, they'll just put it down as 100,000 pascals for atmospheric pressure. So you can look that number up. Now, the volume is in cubic meters or meters cubed. Temperature has to be in Kelvin. Has to be in Kelvin, so we don't end up with any negative numbers because we can't have negative pressure or a negative volume. Absolute zero. Kelvin is zero when we get to the lowest possible temperature. That occurs when the molecules stop moving, and we can find that experimentally if we cool a gas off. The gas will get smaller and smaller and smaller in volume until, if you extrapolate the data, when the volume is zero, then the temperature will be absolute zero. And you can do the same thing for pressure. As you cool a gas off, you'll see that the pressure goes to zero at absolute zero. And we did that in our lab to get an estimate for what absolute zero was. And it was actually pretty close. Number of molecules per mole of a gas is, number of molecules or atoms of a gas we measure in moles, or MOL, moles. N is the number of molecules total. Avogadro's number is this from chemistry, and if you divide the two, you get number of moles. All right, there are two types of problems that we will see that involve ideal gas law. There's single state problems where you'll know three of the variables, and then from those three you calculate the fourth. Or there's a change in state problem where they say, say like the pressure doubles and the volume is tripled. What happens to the temperature where there's a change? All right. So the key thing is to identify which one you have so you know how to approach the problem. If it's a change in state problem, you need to identify the things that are constant so that you can set up your proportionality, and then you know how some variables that are changing, the variables that are changing, how they change the variable we're interested in. Okay, here are 4 ideal gas law problems. I'd like for you to take a look at them and then see if you can solve them by yourself first, and then I'll solve them on paper. All right, let's see how you did. So in our first problem, heat is removed from the sample of gas to the fixed container. There's our volume, so there's V. A graph of the pressure as a function of temperature is shown above. Estimate the number of moles. We're looking for N. What is that? All right, so PV equals nRT. I'm going to go across and pick a number that looks like to be about right there. So I know the pressure is 1, be careful, times 10 to the 5th pascals. Here's our volume. 8 times 10 to the negative 3rd meters cubed equals N, and then R is 8.314 joule per mole Kelvin, and then I'm running out of room, and our temperature is 50 Kelvin. All right, and if we solve that for N, I believe we get something about 1.9 moles. Okay, that is a single state problem. In our next problem, we have a graph that shows the pressure as a function of volume for a sample of gas in a sealed container. It's taken from, okay, sealed container is important. That means the number of moles is constant. It's taken from state X to Y. So volume is changing, so we have a change in volume and we have a change in pressure. And they want to know what's the temperature in state Y. Is it greater than, less than, or the same as X, or can we tell? Well, this is a change in state problem. Okay, so that means, let's see, PV equals nRT. But the number of moles and, of course, ideal gas constant are staying constant. So that means PV is proportional to T. The problem is volume is decreasing and pressure is increasing. So we have two conflicting things, so it is impossible for us to tell what's happening to the temperature. We don't know without more information. Problem 3. We have a sample of gas in a sealed container. Sealed container again means that N is constant. So we're changing P and V as we go along these different routes or pathways. So our initial state is just simply P times V, and that's going to be proportional to our initial temperature. So our temperature at T will be proportional to P times V, and that's our value there. So that's going to be 2P times 1/2 V. That's PV, so that's the same temperature that we started with. If we look at B, B ends up here. That is 3 times the pressure, and that is 3/2 the volume. So that's going to give us 9/2 the new PV, or 9/2 PV. So our temperature has gone up. It's gone up by 4.5 times. All right, let's look at C. C's down here. In this one, we are at 1/3 the original pressure, and we are also at 3/2 the volume. And so what we end up with is these 3's cancel. So we have 1/2 the PV we started with. So this is 0.5 times the original. And then our last one is D over here. And in D, we are again at 1/3 the pressure. And we are at 3 times the volume. They cancel, and we're left with PV. So it's the same temp. Now, what are we supposed to do? Along which process does the gas change the greatest? Well, that would be along path B, because it changes 4.5 times what it originally was. All right, let's look at our last problem, problem number 4. In an experiment, a sample of an ideal gas is taken from state A to B to C to D and then back to A, all the way around. Rank the temperatures of the 4 states. All right. So temperature, again, is proportional to P times V. So let's look at the PV values. The PV value right here is going to be 4 PV. At B, it's going to be 5 PV. At C, it's going to be 2 times 10. So that's 20 PV. And at D, it's going to be 5 times 4. So we got 20 PV again. So our temperature at C will be equal to the temperature at D, which will be greater than the temperature at, what, B is next, which is greater than the temperature at A. A is the coolest. And that's it. Now let's take a look at something called the kinetic theory of gases. All right, so if you look at a gas and look at all the atoms inside, the atoms inside are all moving around at a random rate, in a random direction, at random speeds. They collide with something and then they all change. So it's a constant roiling change of motion. That kinetic energy of the gas molecules, the average kinetic energy of the gas molecules, is equal to 3/2 kBT. Kb, remember, is Boltzmann's constant. And 3/2 is a constant. So T is the only variable on the right. That means that the gas molecules, the kinetic energy of the gas molecules, is proportional to the temperature. So the temperature of an object is a direct measure of the motion, the kinetic energy of the molecules. Now remember that kinetic energy equals 1/2 mv squared. So if we take this and plug it into our equation up here and rearrange it for V, we end up with this thing called VRMS equals the square root of 3 kBT over the mass of the molecules in the gas. But notice, again, we have a couple of constants in this equation, and that means that the RMS velocity is proportional to the temperature divided by the mass of the molecules, square root. So if the temperature goes up, the velocity of the molecules go up. However, if the molecules are more massive, then the velocity of the molecules comes down for the same temperature. But it's not a direct relationship, it's a square root relationship. Now let's talk about this VRMS just for a little bit and this distribution. This is only an average of the kinetic energy. These molecules are moving around at all kinds of random speeds. So we get a random speed distribution. It looks kind of like this. It looks, if you're in statistics, it looks a lot like a bell-shaped curve, but it's not exactly. It stretches out on the right-hand side. So RMS is a way to get an average, to give you an idea of what's going on when the average would be 0. The average speed, or actually the average velocity of the molecules in this room, gas molecules, is 0. So it's kind of like this peak. It's actually a little over to the right. It's not a big deal. Think of it for our purposes as average, okay? So what do we get from all of this? We learned two important things. That first, the molecular mass of the gas molecules makes a difference. This is the speed distribution, number of molecules, and the speed. If you have a high molar mass or atomic mass, then they're going to be skewed down to slower. If you have a low molar mass, say like hydrogen, they'll be skewed out at higher speeds, but they're all going to have, for the same temperature, the same kinetic energy. But the speeds will be different. Kind of like a small moving car, to have the same kinetic energy as a bus has to be going much faster. And then the temperature makes a difference for this distribution. So like if I had room temperature gas, and then I heated it up, then it would move, this peak would move to the right. But it would also move downward because the area in the red here has to equal the area in the green. It's the same number of molecules overall. If we cool the gas down, then it gets scrunched over to a smaller speed or lower speed, and they all get pushed in here, and the peak gets higher. So let's look at a couple of problems. So problem number 5, describe any changes in the kinetic energy of a gas as the gas temperature changes from T to 1/2 T. And then number 6, describe the changes in the motion of the gas molecules as the gas temperature changes from T to 1/2 T. All right. Well, the kinetic energy of the gas molecules are proportional to the temperature. So if we decrease the temperature to half, then the kinetic energy of the gas molecules is also cut in half. The velocity is a little more complicated because it's a square root. But if we cut the temperature in half, we'll have a 2 in the denominator, but it's square rooted. So the velocity will also decrease, but it will decrease or be divided by a factor of square root of 2. All right. I'd like for you to try this one on your own, see if you can sketch these. Sketch the speed distribution for a couple of moles of neon gas at a temperature of 300 Kelvin on a horizontal axis representing the speed of the neon molecules. The vertical axis is the number of neon molecules moving at that particular speed. And then 8 asks for, okay, repeat the same thing for helium. And 9 says repeat the same thing for argon. Make sure that they're in correct relationship to your original neon. All right, our distribution should look like this. So hydrogen, sorry, not hydrogen, helium is going to be skewed to the right as a lower mass, so it's going to have an overall faster speed for the same number of moles for the same temperature. Neon is going to be scrunched over because it is more massive. Argon's even more massive, and if we did xenon, it would be scrunched even farther to the left. Lower velocity, same kinetic energy. All right, let's look at questions 10 and 11. I'd like for you to read these two, see if you can solve them, and then move forward in the video. So pause the video first. All right, so our answer is that we have in air, we have nitrogen and oxygen. It's enclosed in the room, they're at the same temperature. If they're at the same temperature, then they have to have the same average kinetic energy, period. Doesn't matter what their mass is. However, the nitrogen has less mass than oxygen does. So nitrogen will have a higher velocity than the oxygen molecules. All right, here's number 12. These are our final examples. In number 12, we have a fixed amount of an ideal gas and is kept in a container of fixed volume. So the volume's not changing and the number of molecules is not changing. The container is submerged in a bath of hot water that is twice the temperature of the container. So it's going to heat up. Sketch the following graphs and indicate the initial and final states of the gas. All right, pause the video, take your best guess at all the sketches, and then advance the video. So let's check how you did. So here are our answers. A couple things to note right off the bat is the number of moles are staying constant. So as the temperature goes from low to high, the moles don't change. That is also true of the volume. The volume is a constant. So as the temperature rises, PV equals nRT, since everything else is held constant, the pressure will also go up. Let's see what else. Let's talk about the kinetic energy right here. The kinetic energy is directly proportional to the temperature. So as we start at a low temperature and the temperature increases, we'll get a line that looks linear And it should be directly proportional, like it's coming from 0, 0. The temperature as it relates to the speed or the average speed of the molecule is a little more complicated. Remember that that's a square root relationship, so we should have a square root looking curve that should, if it bends right, go down through 0, 0 eventually. But we begin up here at a temperature higher, so it has this bend. But our last one is the fact that we begin at a cold state and we end at a hot state. And so our initial state has the speed of the molecules bunched down to the left. And then as it gets warmer, the molecules spread out more to the right. And there we go. For our last set of questions, I'd like for you to take a look at them, pause the video, and then try to work them yourselves. Problem 13 says, what's the greater force on the sides of the container? In which one, gas X or gas Y? So we take a look at it. Remember that force equals pressure times area. So how are we going to find the pressure? Well, remember PV equals nRT. They have the same temperature. R is the same, of course. Identical containers, so same volume. And the same number of molecules. Hey, so they have the same pressure. And since the containers are identical, pressure and area is the same, so the force is the same for both. There we go. Our second question says, or question 14 says, in which sample is the average speed of the molecules greater? Remember that velocity is proportional to the square root of the temperature over the mass of the molecules. All right, and we just established that the temperature is the same in both of the gases, so therefore they're both the same as well. That was too easy. Problem 15 will challenge us a bit more. So in this one, we have a gas molecule that's moving towards a wall and bouncing off. There's actually a lot of gas molecules doing this, and they're in random motion, of course. Molecules have a mass of m, and they have a velocity of v, an average velocity of v, and they're hitting the wall for a period of time. So this is our velocity this way. Now, question 5 says, explain why only the perpendicular component of the velocity to the wall, v sub perpendicular, changes when the gas molecules or the gas atoms collide with the wall. All right, so if we take a look at this, you see that we have both a, say in this case, a perpendicular part of the velocity and a parallel part of the velocity to the wall. Since this is an elastic collision, all these atomic collisions with the wall for a gas are going to be elastic. So it's going to bounce off the wall without losing any speed, and it's going to bounce off at the same angle. So this angle here is the same angle here. So this is the perpendicular velocity, and this is the parallel velocity. Now, they look like nothing's changed, but this one indeed hasn't changed at all. But the perpendicular component has. And so if we call to the right positive, our change in velocity equals our final velocity, which is to the left. Remember, it's v final, so v perpendicular negative to the left, minus the initial, which is v perpendicular. So we get a -2 v perpendicular change. So it changes because it bounces into the wall and bounces back. But in this case, the parallel part are in the y direction in my drawing. It's not changing at all. So only the perpendicular part changes. All right, how about number 16? Derive an expression for the force imparted on the wall by a single gas molecule. All right, well, in number 16, remember that F equals ma. But A equals delta V over delta T. So this is the mass of our molecule, and this is our delta T. Now I'm just going to take the absolute value because it's just asking for how big the force is. We don't really care about the direction. So this would be 2V perpendicular divided by T. And that's our force from a single molecule hitting the wall. The next question says, derive an expression for the pressure. Well, remember, pressure is equal to force over area, Well, we have a force of 2mv perpendicular over t, and that would be divided by the area itself, but this is only for one molecule, so we need to multiply it by all of the molecules that are there. So that would be the total number of molecules, and that would be the pressure on the wall for the time period t for all of the molecules colliding with the wall. In question number 18, we have a sample of gas that begins at point A, it ends at state B, but it can go through either point X up here or point Y as shown. And the question is, which process will result in the greatest change in temperature? All right, well, PV equals nRT. So let's find out the initial temperature. The initial temperature over here at point A would be temperature equals PV over nR. So for A, that would equal, let's see, P naught V naught over nR. And the temperature for B would equal, let's see, we got 4 P naught 2 V naught over nR, which is the same. So look, this is 8 P naught V naught over nR. So the temperature has gone up 8 times. So this spot right here has a temperature 8 times greater than that one. So TB equals 8 TA. But wait, does it matter which pathway we take? Did we say anything about the pathway at all? No, it makes no difference. So they both have the same exact change in temperature. Pathway is irrelevant. All that matters is where we started and where we ended for temperature. For our last problem, we're going to crunch some numbers. We have a cylindrical container filled with a gas, as I've shown here. It's in a room with standard atmospheric pressure. So out here we have standard atmospheric pressure, which by the way is 100,000 pascals on the AP exam. The container and the gas have these properties. So here's all the properties we have. Calculate the minimum upward force that needs to be applied to lift the lid off the container. So what we're trying to do is lift this lid. So let's see, there's going to be a force downward from the atmosphere. There's going to be a force downward because the thing has weight. So I'm just going to call that mg. This is actually equal to mg already. It's in newtons. And then we have a force upward from the gas itself. There will be our force up to lift it. So in order to lift this, these two here have to be at least as big as these two. So I'm just going to set them equal. Or what I can do is the force that I have to lift up equals mg plus force from the atmosphere minus the force from the gas. Now, remember the force is equal to pressure times area. So these are both going to be pressure from the atmosphere times the area minus the pressure from the gas times the area plus mg. And I'm going to factor out this area, so I'm left with mg minus the area times the difference in pressure, pressure from the atmosphere minus the pressure inside the gas. Now, let's see, how many of these things do we know? We know this is 800. We know the area, good. We know the pressure of the atmosphere, good. And we don't know the pressure inside the gas, so it looks like we're going to have to calculate that, which is a bummer. So here we go, little sidebar. PV equals nRT, or P equals nRT over V. And if we plug in, let's see, do we all know all these things? Do we know the number of moles? Yes. R we know, temperature we know, volume we know. All right, so we take the numbers that we have and plug them in here. There's going to be a little bit of math, and you'll end up with approximately 80,000 pascals from all this information. So now we're able to finish our problem here. We have 800 newtons here minus the area, which is this number, 0.935 meters squared. And our atmospheric pressure is 100,000. Our pressure inside the gas is 80,000. So that's a difference of 20,000 pascals And if we finish this math out, we get a force of about 19,500 newtons necessary to lift the lid off of the container. Now, some of you may have witnessed this trying to unscrew a lid on a jar sometimes. And if you crack the seal, it's easier to take the lid off because you don't have this difference in pressure from the atmosphere pushing it down onto the jar. That's it. That's our review of gases. Our next video will be thermodynamics.